Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family: Jackie, Mike, Athena, Lisa, Josie, and Spain. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener supported and ad-free for everyone, and it's very much appreciated. If you're interested in supporting Boring Books for Bedtime and finding out more about the perks available to subscribers, including exclusive episodes heard nowhere else, you'll find a link to Patreon in the show description. You'll also find a link to buymeacoffee.com where you can support us with a one-time tip. No subscription required. I hope you'll take a moment to check them out. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight, let's continue with a very interesting astronomical book, Mars and Its Canals, by Percival Lowell, Director of the Observatory at Flagstaff, Arizona, non-resident professor of astronomy at the Massachusetts Institute of Technology, fellow of the American Academy of Arts and Sciences, etc., etc. First published in 1906 by the Macmillan Company, New York and London. Let's pick up right where we left off in Chapter 5. Behavior of the Polar Caps. Let's begin. To explain these interesting diversities of behavior in the several polar caps, we shall have to go back a little in general physics in order to get a proper takeoff. It is a curious concomitant of the law of gravity that the amount of heat received by a planet in passing from any point of its path to a point diametrically opposite is always the same, no matter what be the eccentricity of the orbit. Thus, a planet has as many calories falling upon it in traveling from its vernal equinox to its autumnal as from the autumnal to the vernal again, although the time taken in the one journey be very different from that of the other. This is due to the fact that the angle swept over by the radius vector, that is, the imaginary bond between it and the sun, is at all points proportional to the amount of heat received. Just as it is of the gravity undergone, the two forces radiating into space as the inverse square of the distance. Thus the heat received by a point or a hemisphere through any orbital angle is independent of the eccentricity of the orbit. But it is not independent of the axial tilt, for the force of the sun's rays is modified by their obliquity. The amount of heat received at any point in consequence of the tilt turns upon the position of the point, and for any hemisphere taken as a whole, it depends upon the degree to which the pole is tilted to the source of heat. In consequence of being more squarely presented to its beams, the hemisphere which is directed toward the sun, and therefore is passing through its summer season, gets far more insolation than that which is at the same time in the depth of its winter. For a tilt of 24 degrees, the present received value for the axis of Mars, the two hemispheres so circumstanced get amounts of heat respectively in the proportion of 63 to 37. But though the summer and winter insolation thus differ, they are the same for each hemisphere in turn. Consequently, the mere amount of heat received cannot be the cause of any differences detected between the respective maxima and minima of the two polar caps. If heat were a substance which could be stored up instead of being a mode of motion, the effect produced would be in accordance with the quantity applied, and the two caps would behave alike. As it is, the total amount has very little to say in the matter. Not the amount of heat, but the manner in which this heat is made at home is responsible for the difference we observe. Now, though the total amount is the same in passing from the vernal to the autumnal equinox, as from the autumnal to the vernal, the time during which it is received in either case varies from one hemisphere to the other. It is summer in the former while it is winter in the latter, and the difference in the length of the two seasons due to the eccentricity of the orbit makes a vast difference in the result. Winter affects the maxima, summer the minima attained. Of these opposite variations presented to us by the two caps, the maxima, the one most difficult to detect, is the easiest to explain, for the difference in the maxima seems to be due to the surpassing length of the Antarctic night. Owing to the eccentricity of the orbital ellipse pursued by Mars and to the present position of the planet's solstices, the southern hemisphere is farther away from the sun during its winter and is so for a longer time. The seasons are in length for the northern hemisphere: spring 199 days, summer 183 days, autumn 147 days, and winter 158 days, while for the southern hemisphere they are spring 147 days, summer 158 days, autumn 199 days, and winter 183 days. The Arctic polar night is thus 305 of our days long, the Antarctic 382. Thus, for 77 more days than happens to its fellow, the southern pole never sees the sun. Now, since the total sunlight from equinox to equinox is the same in both hemispheres, its distribution by days must be different. In the southern hemisphere, the same amount is crowded into a smaller compass in the proportion of 305 to 382, that being that hemisphere's relative ratio of days. But since during winter the cap increases, there is a daily excess of accumulation over dissipation of snow, and each 24 hours must on the average add its tithe to the sum total. Since the northern days are the warmer, each adds less than do the southern ones, and furthermore, there are fewer of them. On both these scores, the amount of the deposition about the northern pole should be less than about the southern one. Consequently, the snow sheet there should be the less extensive and show a relatively smaller maximum, which explains what we see. With the minima, the action is otherwise. Inasmuch as the greater heat received during the daylight hours by the southern hemisphere is exactly offset by the shortness of its season, it would seem at first as if there could be no difference in the total effect upon the two ice caps. But further consideration discloses a couple of factors which might, and possibly do, come in to qualify the action and account for the observed effect. One is that though the total amount of heat received is the same, the manner of its distribution differs in the two hemispheres. In the northern one, The time from vernal to autumnal equinox is 382 days against 305 in the southern. Consequently, the average daily heat is then 5/4 more intense in the southern hemisphere. Indeed, it is even greater than this, and nearer 4/3, because the melting occurs chiefly in the spring and in the first 2 months of summer, when the contrast in length of season between the two hemispheres is at its greatest. Now, a few hotter days might well work more result than many colder ones, and this would be particularly true of Mars, where the mean temperature is probably none too much above the freezing point to start with. Ice consumes so much caloric in the process of turning into any other state, laying it by in the form of latent heat before it can turn into water, and then so much more before this water can be converted into steam, that a good deal has to be expended on it before getting any perceptible result. Once obtained, however, the heat is retained with like tenacity, so that the process works to double effect. If sufficient heat be received, the ice is first melted, then evaporated, and finally formed into a layer of humid air, the humidity of which keeps it warm. Dry ice is unretentive of heat, moist air the opposite. And for the melting of the ice cap to proceed most effectively, the temperature that laps it about must be as high as possible and kept so as continuously as may be. If between days it be allowed to fall too low at night, much caloric must needs be wasted in simply raising the ice again to the melting point. This a blanket of warm air tends to prevent, and this again is brought about by a few hot days rather than by many colder ones. It is not all the heat received that becomes effective, but the surplus heat above a certain point. The gain in continuity of action thus brought about is somewhat like that exhibited between the running of an express and an accommodation train. To reach its destination in a given time, the former requires far less power because it does not have to get up speed again after each arrest. Thus the whole effect in melting the snow would be greater upon that hemisphere whose summer happens to be the more intense. The greater swing in size of the cap most exposed to the effects of the eccentricity is, then, the necessary result of circumstances when the precipitation is not too great to be nearly carried off by the subsequent dissipation. This is the state of things on Mars, and the second of the factors above referred to. On the Earth, as we have seen, the polar caps are somewhat larger at their maximum, and very much so at their minimum. Now, this is just what should happen where the precipitation increased. Suppose, for example, that the amount of precipitation were to increase while the amount of summer melting remained the same, and this would be the case if the vapor in the air augmented for one cause or another, and the result of each fresh deposit was locked up in snow. After a certain point, the cap would grow in depth rather than in extension. The winter deposit would be thicker, but the summer evaporation would remain the same. Now, if this occurred, it is evident that the minimum size of the cap would increase relatively much faster than the maximum, and furthermore, that the relative increase of the minimum in the two caps would be greatest for that which had seasons of extremes. The result we see in the case of the Earth. In the Arctic cap, where in consequence of the eccentricity of the orbit the winter is shorter, the maximum is less than in the Antarctic, and this extra amount of precipitation cannot be wholly done away with in its intenser summer, so that the minimum too is greater there. We reach then this interesting conclusion. We find that eccentricity of orbit by itself not only causes no universal glaciation in the hemisphere, which we should incidentally suppose likely to show it, but actually produces the opposite result in more than offsetting by summer proximity what winter distance brings about. To cause extensive glaciation, we must have, in addition to favorable eccentricity, a large precipitation. With these two factors combined, we get an ice age, but not otherwise. The result has an important bearing on geologic glacial periods and their explanation. Once formed, an ice sheet cools everything about it and chills the climate of its hemisphere. It is a perpetual storehouse of cold. Mars has no such general glaciation in either hemisphere, and the absence of it, which is due to lesser precipitation, together with the clearness of its skies, accounts for the warmth which the surface exhibits, and which has been found so hard hitherto to interpret. Could our Earth but get rid of its oceans, we too might have temperate regions stretching to the poles. Chapter 6. Martian Polar Expeditions. Polar expeditions exert an extreme attraction on certain minds, perhaps because they combine the maximum of hardship with the minimum of headway. Inconclusiveness certainly enables them to be constantly renewed without loss either of purpose or prestige. The fact that the pole has never been trod by man constitutes the lodestone to such undertakings, and that it continues to defy him only whets his endeavor the more. Except for the demonstration of the polar drift current, conceived of and then verified by Nansen, very little has been added by them to our knowledge of the globe. Nor is there specific reason to suppose that what they might add would be particularly vital. Nothing out of the way is suspected of the pole beyond the simple fact of being so positioned. Yet for their patent inconclusion, they continue to be sent in sublime superiority to failure. Martian polar expeditions, as undertaken by the astronomer, are the antipodes of these pleasingly perilous excursions in three important regards, which, if less appealing to the gallery, commend themselves to the philosopher. They involve comparatively little hardship. They have accomplished what they set out to do, and the knowledge they have gleaned has proved fundamental to our understanding of the present physical condition of the planet. The antithesis in pole pursuing between the two planets manifests itself at the threshold of the inquiry in the relative feasibility with which the phenomena on Mars may be scanned, for curiously enough, instead of being the pole and its surrounding paleocrystic ice, which remains hidden on Mars, it is rather the extreme extent of its extension and the lowest latitudinal deposit of frost which lies shrouded in mystery. The difficulty there is not to see the pole, but to see in winter the regions from which our own expeditions set out, and this because the poles are well displayed to us at times which are neither few nor very far between, while favorable occasions for marking the edge of the caps when at their greatest have neither proved so numerous nor so favorable. The tilt of the planet's axis, when conveniently placed for human observation, has been the cause of the one drawback. The planet's meteorological condition in those latitudes at that season, the reason for the other. What knowledge we have of the size of the caps in degrees upon the surface of the planet At this, their extreme equatorward extension has been given in the last chapter. Their aspect at the time, together with what that aspect betokens, was not there touched upon. With it, therefore, and the peculiarities it presents to view, we shall begin our account of the cap's annual history. When first the hemisphere, the pole of which has for half a Martian year been turned away from the sun, begins to emerge from its long hibernation, the snow cap which covers it down even to temperate regions presents an undelimited expanse of white, the edges of which merge indistinguishably into the groundwork color of the regions round about. Of a dull, opaque hue along its border, its contour is not sharp, but fades off in a fleecy fringe without hard and fast line of demarcation. Such notably was the aspect of the North Temperate Zone in 1896, when, tilted as it then was away from us into a mere northern horizon of the planet's limb, it showed prior to the definite recognition of the North Polar Cap in August of that year, and such too was the look of the disk's southern edge, both before and after the first certain detection of the southern cap in 1903 and 1905. Each was then in the depth of winter, for in Martian chronology, the season corresponded in each at that time to what we know in our northern hemisphere as the latter part of February and the early part of March, and the appearance of the planet's surface in both was not unlike what we know at the same season in latitude 45 degrees. Indeed, there is reason to suppose bad weather there then, and the extreme fringe, from the pale tint it exhibited, to have been cloud rather than snow. It is quite in keeping with what we know on Earth, or can conceive of elsewhere, that such aspects should characterize the cap at or near the attainment of its greatest development. Whether it were not yet quite arrived at this turning point of its career, or had but slightly passed it, a vagueness of outline would in either event proclaim the fact. For were the frost still depositing, the cap's edge would show indefinite, and on the other hand, had it just begun to melt, evaporation would give it an undefined edge before the melting water had gathered in sufficient quantities to be itself noticeable. Its behavior subsequent to recognition bore out the inference from its aspect when it first appeared, while for many days prior to its coming unmistakably into view, it was impossible to say whether what was seen of the southern cap in 1903 and 1905 was cloud or snow. So even after it had definitely disclosed itself, it continued to play at odds with the observer. Showing sharp at the edges one day, it would appear but hazily defined the next, thus clearly demonstrating itself to be at the then unstable acme of its spread. Such a state of things we are only too familiar with in our own March weather, when after days of sunshine that have melted off the winter's white and fringed it with rivulets and awakening grass, a snowstorm falling upon it powders the ground again that was beginning to be bare, and at one stroke extends the domain of the snow, while mystifying the actual limits it may be said to occupy. The same condition of things, then, is not unknown on Mars, and to fix the precise date of so wavering a phenomenon is not so much matter of difficult observation as of physical impossibility. Nor is the southern cap, at this the height of its winter expansion, confined strictly to its own proper limits. Faint extensions, now so connected with its main body as to form part and parcel of it, now so detached and dull of tint as to make the observer doubtful of the exact relationship are generally to be seen attendant on it. Hellas in winter is much given to such questionable garb, and has in consequence been mistaken by more than one observer for the cap itself, appearing as it does well upon the southern limb, and being often the only region to show white. Indeed, frost-bound as it then is, to consider it the polar cap, though possibly geographically incorrect, may climatologically be sustainable. Its northern extremity extends down to latitude 30 degrees, a pretty low latitude for frost. Still, such equatorward extension is not without corroborating parallel. In 1903, at what was in Martian dates April 26th, the whole of the region south of the Solus Lacus and the Nectar showed white, with a whiteness which may as well have been hoarfrost as cloud. Now, the Nectar runs east and west in latitude 28 degrees, so that in this instance, too, it is possible that Arctic conditions knocked at the very doors of the tropics. Encroachment of the sort is equivalent to snow in Cairo, and permanent snow at that. Not an occasional snow flurry, but something to linger on the ground and stay visible 60 millions of miles away. Knowledge of either cap in this the midwinter of its year has been a matter of the most recent oppositions of the planet. Up to within the last few years, our acquaintance with either cap was chiefly confined to the months, one might almost say the weeks, immediately surrounding the summer solstice of its respective hemisphere. The behavior of the caps during the rest of their career was largely unknown to us, from the very disadvantageous positions they occupied at the times the planet was nearest to the Earth. Beginning with 1894, however, our knowledge of both has been much extended by a proportionate extension of the period covered by the observations. It used to be thought impracticable to observe the planet far on either side of opposition. Now it is observed from as much as 4 months before that event to the same period after it. The result is a systematic series of observations which in many ways has given unexpected insight into Martian conditions. One of the benefits secured has been the lengthening of the period of study of the cap's career, a pushing of inquiry farther back into its spring history, and a longer lingering with it in its autumnal rebuilding. Yet up to the very last opposition, a gap in its chronology still remained between February 25th and April 1st. The opposition of 1905 has bridged this hiatus and brought us down to the latter date at which the melting of the cap begins in earnest. From this point, April 1st on, we have abundant evidence of the cap's behavior. Its career now for some time is one long chronicle of contraction. Like Balzac's Peau de Chagrin, it simply shrinks, giving out of its virtue in the process. The cap proceeds to dwindle almost under the observer's eye, till from an enormous white counterpane spread over all the polar and a large part of the temperate zone, its area contracts to but the veriest nightcap of what it was before. From 70 degrees across it becomes 60, then 50, then 40, till by the middle of the Martian May it has become not more than 30 degrees in diameter. During this time, from the moment the melting began in good earnest, the retreating white is girdled by a dark band of a blue tint, which keeps pace with the edge of the cap, shrinking as it shrinks, and diminishing in width as the volume of the melting decreases. After the melting has been for some time underway and the cap has become permanently bordered by its dark blue band, a peculiar phenomenon makes its appearance in the cap itself. This is its fission into one or more parts. The process begins by the appearance of dark rifts, which, starting in from the cap's exterior, penetrate into its heart until at last they cleave it in two. Rifts have been seen by several observers and in both caps, and what is most suggestive, they always appear in the same places year after year. Sometimes oppositions elapse between the several detections, for they are not the least difficult of detail, but when they are caught, they prove to lie just where they did before. The permanency in place of the rifts, a characteristic true of them all, shows them to be of local habit. Thus the rift of 1884 and 1897 reappeared again to another observer in the same position in 1901. They are therefore features of, or directly dependent on, the surface of the planet. But it will not do from this fact to infer that they are expressive of depressions there. The evidence is conclusive that great irregularities of surface do not exist on Mars. As we shall see when we come to consider the orology of the planet, it is certain that elevations there of over 2,000 or 3,000 feet in altitude are absent. Differences of temperature, able to explain a melting of the ice in one locality, coincidentally with its retention in an adjacent one, must in consequence be unknown, and this much more conclusively than at first appears, for the reason that the smaller the planet's mass, the less rapidly does its blanket of air thin out in ascent above the surface. This is in consequence of the greater pull the larger body exerts, and the greater density it imparts to a compressible gas like our atmosphere. Gravity acts like any force producing pressure, and by it the envelope of air is squeezed into a smaller compass. But as this is done throughout the atmospheric layer, it means a more rapid rarefaction as one leaves the body. The action is such that the height necessary to reach an analogic density varies inversely as the gravity of the mass. In consequence of this, to compass a relative thermometric fall, for which a moderate difference of elevation would suffice on Earth, an immoderate one must be made on Mars. For gravity there being but 3/8 what it is here, 8/3 the rise must be made to attain a proportionate lowering of temperature. This fact renders the above argument against elevation and depression, being the cause of the phenomenon, 3 times as cogent as it otherwise would be. With so gradual a gradient in barometric pressure there, and so low a set of contour lines, altitude must be a negligible factor in Martian surface meteorological phenomena. Both density and temperature can be but little affected by such cause, and we must search elsewhere for explanation of what surface peculiarities we detect. Meanwhile, the rifts themselves, from being lines which penetrate the cap from its periphery in toward its center, end by traversing it in its entirety and separating portions which, becoming outlying subsidiary patches, themselves proceed to dwindle and eventually disappear. The rifts usually take their rise from such broader parts of the cap encircling blue belt as make beads upon that cordon, and are clearly spots where the product of the melting of the cap is either specially collected or produces its most visible effect. So far the description might apply with substantial accuracy to either cap, yet the conduct of the two is in some ways diverse and begins to accentuate itself from this point on. From the time that the North Polar Cap reaches a diameter of about 25 degrees, a singular change steals over it. From having been up to then of a well-defined outline, it now proceeds to grow hazy and indistinct all along its edge. This change in its character at the same period of its career has been quite noticeable at each of the three last oppositions, so that small doubt remains that the metamorphosis is a regularly recurrent one in the history of the cap. Coincident with the obliteration of its contour, its dimensions seemingly enlarge. It is as if a hood had been drawn over the cap of a dull white, different from the dazzling brilliance of the cap itself, and covering more ground. Such is probably what occurs, with vapor for veil. The excessive melting of the cap produces an extensive evaporation, which then in part condenses to be deposited afresh, in part remains as a covering, shutting off from our view the outlines of the cap itself. It would seem that at this time the cap melts faster than the air can carry it off. A sort of steaming appears to be going on, taking place in situ, for it clearly is not wafted away. The time of its coming, too, is significant, for the season is May 15th, the height of time for a spring haze to set in. Then later it dissipates with the same quiet indefiniteness with which it gathered. It is some time in Martian June before the spring haze clears away, and when it does go, only a tiny polar cap stands revealed beneath it, from 6 to 8 degrees across, or from 1/10 to 1/15 of what it was when it passed into its curious spring chrysalis. The date of emergence varies. In 1903 it occurred early, the haze not being marked after June 3rd, though recurring again at intervals for a day or so. In 1905 it was later, perceptibly thin after June 21st. It did not certainly clear away until July 9th and came back again on July 16th and possibly on the 25th. These vicissitudes of aspect give us glimpses into a sweet unreasonableness in Martian weather, which makes it seem more akin to our own, and this on two counts, diurnal and annual. From day to day, atmospheric conditions shift for purely local cause, while, furthermore, successive Martian years are not alike. In some, the season is early, in others late, so that Mars is no more exempt than are we from the wantonness of weather. Clearly disclosed, thus reduced to its smallest possible terms, it remains for some months of our days, for 6 weeks of its own. During that period it continues practically unchanged, neither increasing nor decreasing significantly in size, nor altering notably in aspect. Measures of the drawings of it then make it from 5 to 8 degrees across, and it is possible that it really fluctuates between narrow limits, though its clear-cut outline at all times renders the variation difficult to explain. We are not so near it as we could wish, for on these occasions, even at their best, it is over 200 times as distant as the moon, and the greatest magnification possible still leaves it 100,000 miles away. To the South Polar Cap a somewhat similar history attaches, but with a difference. In its case, no such regularly recurrent spring haze has yet been noted. The melting of this cap would seem to be of a more orderly nature than its fellow, and not to outdo what can conveniently be carried off. Its summer also is shorter than the Arctic one, so that it has the less time to dispose of its accumulations. The only other respect in which it seems to be differently circumstanced from its antipodes is in the character of its surroundings. About it are large blue-green areas, which with intermission stretch down in places to within less than 10 degrees of the equator, whereas the other pole is continuously circled for long distances by practically uninterrupted ochre. The character of the environment seems thus the only thing that can account for the difference in behavior, and this proves the more plausible when we come to consider what those two classes of regions respectively represent. In other ways as well, the southern cap is the more self-contained. The rifts indeed break it up into separate portions, and these in part remain as outlying detachments of the main body, as was notably the case in 1877 and in 1894, but they hardly have the permanency and importance of those similarly formed about the Arctic pole. Nothing Antarctic, for instance, compares with the subsidiary patch in the North Polar regions, lying in longitude 206 degrees, which both in Schiaparelli's time and during the late oppositions as well, was almost as fixed a feature of the Arctic zone as the cap proper. Not quite so constant, however, and not so solid-looking a landmark is this patch for all its extent, which nearly equals the area of the more legitimate portion. It bears on its face a more pallid complexion, as if it were thinner, and this is borne out by the fact that it occasionally disappears, an event which so far at least has never befallen the northern cap itself. Less constant the southern one is to its own minimum than the northern. In some seasons, in most in fact, it reaches like the other a more or less definite limit of diminution, which it does not pass, but this is not always the case. In 1894 it disappeared entirely at the height of its midsummer. The season was probably unusually hot then in the southern hemisphere of Mars. In position, the caps have something to say about physiographic conditions. Both caps at their minima are then irregular, and the center of the south one is markedly eccentric to the areographic pole. It lies some 6 degrees north along the 30th meridian. The northern one is also probably eccentric, but much less so, with a divergence not much exceeding a degree and of doubtful orientation. Not only are both caps not upon their respective poles, but they are not opposite each other, the one lying in longitude 30 degrees and the other in 290 degrees. This speaks, of course, for local action. In some wise this must depend on the configuration of the surface, yet so far as markings go, there is nothing to show what the dependence is. The excentring of the caps is paralleled by the like state of things on Earth. The pole of cold does not coincide in either hemisphere with the geographic pole. On the Earth its position is largely determined by the distribution of the land masses. Continents are not such equalizers of heat as oceans because of their conductivity on the one hand and their immobility on the other. In winter, they part with their heat more quickly, and convection currents cannot supply the loss. This accounting for thermal pole eccentricity is inapplicable to Mars because of the absence there of bodies of water, and it is significant that the degree the earthly poles of cold are out much exceeds what is the case on Mars. Possibly areas of vegetation there replace to some effect areas of water. It is certainly in favor of this view that the Arctic regions there are more desert than the Antarctic, and that the North Pole of cold occupies more squarely the geographic pole. Not till 1903 did the actual starting again of either cap chance to be seen, nor was this indeed a matter of hazard, but a persistent inquiry, by observation prolonged, after the planet had got so far away that its scanning had hitherto been discontinued. Such search beyond the customary limits of observation was essential to success, because of the relation of the axial tilt to the position of the planet in its orbit. At an opposition well placed for nearness, the tilt is such as largely to hide the pole, and to present the polar regions too obliquely to view for effective scanning. This is true both of the Arctic and the Antarctic regions in turn. For the Martian axis being inclined somewhat as our own is to the plane of the planet's orbit, we at times see well and at times but poorly the Arctic or Antarctic zones. The cap, the starting to form of which was thus caught, was the Arctic one, the date 128 days after the northern summer solstice, or thereabouts, for as is perhaps natural, the advent of the phenomenon partook of the wave-like advance of such things, familiar on Earth, an advance succeeded by a recession and then followed by another advance. So much is proof of local weather there as here. Hoar frost was successively deposited and then melted off. What is significant, the deposition of the frost took place simultaneously over large areas. The very first patch of it, in about longitude 320 degrees, extended at one stroke down to latitude 55 degrees, for it actually crossed the Pierius somewhat to the south. A second patch stretched to the east of the cap. 2 wings these made to the kernel of cap itself. Through the wings could be marked the line of the canal, the Pierius upon the one side, the Anepius upon the other. Such visibility of the canals through the white stretches proved the white not to be due to clouds suspended between us and them, but a surface deposit which found no lodgment upon the canals themselves. The same avoidance of dark markings was evidenced by the showing of the dark rim round the cap's kernel. Now, if the deposit were indeed hoarfrost, this failure to find permanent foothold on the dark markings is what we should expect to witness, for whether they were vegetation or water, equally in either case the frost would melt from them first. Probably they were both vegetal, though some doubt might exist about the latter, the band around the kernel. It was then August 20th in that hemisphere. Such deposition over great stretches of country is perhaps not so surprising as it appears at first sight, when seen from without in its totality. After all, something not unlike it occurs in our snowstorms, when hundreds of square miles are whitened at once. Furthermore, with an atmosphere as thin as Mars seems to possess, the temperature must be perilously near the freezing point in the Arctic and subarctic regions at the close of summer. Steadily, with intermissions, the white sheet increased until even the dark border of the cap became obliterate, the kernel showing at first through the veil like the ghost of what it had been, and then ceasing to be visible at all, its delimitations being buried under deeper and deeper depositions of frost. The perennial portion of the cap was thus merged in the new fallen snow. This marked the oncoming of the Arctic winter in full force, and happened even before the polar sun had wholly set, for the pole did not enter into the shadow till 2 of our months later, the autumnal equinox occurring 183 days after the summer solstice, or 55 days after the first fall of frost. Then the pole passed into its star-strewn Arctic night, a polar night of twice the duration of our own, and the circumpolar regions entered upon their long hibernation of 10 of our months. And with the end of Chapter 6, I think we'll end this evening's reading from Mars and Its Canals by Percival Lowell. That was certainly a lot of information about the poles, which is all very interesting, but I kind of wish he'd get to the canals part, maybe in our next reading. If you'd like to read this work for yourself and see Lowell's sketches of Mars as seen through his telescope, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.